So we can go on to sequence types. Okay, great. Okay. So we'll all should be pretty comfortable with the idea of individual scalar types, numbers, characters, so forth. So mostly what you'll be dealing with in, like I said, either CompuCell or Tellurium is you'll be dealing a lot with sequence types. So in CompuCell, you'll be dealing with lists of cells and neighbors and other things like that. In Tellurium, we'll be dealing mostly with vectors and matrices. And then the thing we'll be doing in matrices is treating them as a sequence. We're basically going over all of the rows in a matrix, or all the columns in a matrix, or all of the numbers in a list. We're doing a lot of that. So good to know how to create sequences and how to manipulate them and so forth. So how do we create sequences? Well, the most basic one that we've already encountered quite a bit is strings. So a string, again, it's S equals quotes, some stuff. Okay. Now, when we can use these square brackets to create a list of objects. So you can do L equals square bracket. 1, 2, 3, 4, 6. Okay, great. That's a list of numbers. We also have tuples. Tuples are pretty similar lists in that they are an ordered sequence, but the big difference between a tuple and a list is a tuple is immutable, meaning that once we create a tuple, you cannot change the elements in that tuple. So we can do T equals 1, comma. And both tuples and lists, they both have roles that they're intended for. So if we want to access individual elements out of them, so one function that we can use to act on them is the length. So we can do len L 6, len T gives me the length. Okay. Slicing, okay. So now we get to actually access the elements in a sequence. So to access an item in a sequence, we use the square bracket syntax. So we can do L 0. Okay. Python uses what's called zero-based indexing, where the first element in that sequence has a 0 index. So we can do L1, L2, that accesses the individual elements in there. T0. So we had our string here, S0, S8. Okay. We can set values in a list. So you can do L0 equals 5. But a tuple and a string, remember, they're immutable. So if we try to do T, nope, can't do that. Tuple does not support assignment. In a string, string does not support assignment. Okay, so that means once I've created a string or a tuple, I cannot actually change the individual elements in that. I can access them, I can read them, but I cannot write the individual elements in there. Okay. So the slicing, that is one of the most powerful things in Python, and we will be using these all the time in Thorium. Okay. So a slice operates really similarly to a range, okay, where we have the exact same idea, where we have a start value, a stop value, and a step value. Okay. And what a slice does, it's essentially what it sounds like. So a slice gives you a slice or a subset of a sequence. We have my L. So we can do L, and I want to slice from 0 to 3. That gives us the elements 0, 1, and 2. The first 3 elements in there. Okay. If we want to, let me go ahead and make it, let me make a bigger list. L, list, range. Just using range because I'm lazy to type. Okay. So we have all the numbers 0, 1, 2, 3, 4 up to 9. Okay. So we can do L. Okay. And then we can do from 3 to 6 in steps of 1. Oops. In steps of 2. Okay. All of these values, start, stop, and step, they all have defaults, okay? So the default value for start is 0. It's the start of the array or the list. The default value for stop is the end of the list. The default value for step is 1. So if I leave everything as defaults, I can do L colon here. Okay. And because of default values, it simply went over every element in there and gave me the entire list back because I just left the defaults alone. Which is identical to this. L 0 colon len okay. So this is identical to this. Okay, defaults. Defaults are important. Remember I showed you how range, we can give a step size of -1. That's a really handy way of getting the items in reverse order. Okay, so we can do L colon -1. Okay, defaults. It does a little bit of a, if you set your step size to negative, it defaults these guys to the end of the list and the beginning. So it does everything in reverse order. So L colon is a list in forward order. L colon -1 is reverse order. And instead of trying, I strongly suggest you do not try and remember these colon. Don't remember that. Only thing you have to remember is this one basic thing of what do they actually mean. And they mean start, stop, and step. As long as you do those three basic things down, start, stop, and step, you'll be able to whip out slicing really, really easily and quickly. Do the kind of parentheses matter? Yes, because when I'm dealing with a list, the square brackets indicate that I'm dealing. The square brackets indicate that I'm grabbing one or more elements out of the list. But if I try to do L, if I try to do that, okay. In Python, the parentheses, when you call it like print I, okay. The parentheses here, they mean that you want to treat this thing as a function that you're going to call, and these are the arguments to it. However, if you want to access them as the square brackets means we're accessing it as a list. So we can do L, 8, give us the 8th element back. But if we do L, 8, it's not callable. Similarly, if I try to do print 8, well, this is, I've obviously never done this before. It'll say, look at this. So it'll say print, well, I'm sorry, that's not a list. I can't access the items in there. You will rarely encounter objects that support both a parenthesis and a square in that they're both callable and in their list, but those are really, really rare. We're just not going to cover that. Okay. So, okay. Let's do some more examples here. So we can do S equals A, B, C, G. So we did S 4 colon, 4 colon 1. Starting at 4 down to 1 in steps of -2. Okay. So we start at 4. Okay. So we do bump, bump. Got the next one. And we're at the end. Okay. So we did actually pick did some indexing. Negative indexing. Okay, good. So we can do S, index 0, first element. We can also do negative indexing. Negative indexing is where we're counting from the back of the list backwards. Okay. So we can do S, -1. It's G. Okay. So we went to G. S -1 is -1 from the end of the list, which is so the end of the list is 1 past the last element. So 1 before the last element is, or one before the end is the last element. So that's why S -1 gives me the last element in the list. We can do S 2, S 3, S, don't know if this will work, 90. Look at this. So I did -90, it's past the end. So that means we can grab any element in the forward direction or any element in the backwards direction, but you can't actually do the overlapping. Okay. Okay. So let's do an exercise here. let's do an exercise of slicing and combining. So we start off with a string S of 200 letters. I mean, honestly, just either go to Google and grab some random text or just type some random text. Honestly, doesn't matter. And we'll do some slicing. Okay. So we'll do S equals we got a string. So we want a slice of the string from indices A through D and D through D with a space. So in my list here, I want to pick up some and, okay? So honestly, the best way to do learn about slicing is experiment, play. So we can do S, and then I can do, that looks like about a 10. Seven, one more, some, and that's it. Okay. Some, okay, great. And then I can do S. Okay, good. Okay. And then, simply do, since I figured out the indices, I can do print S plus. We can do arithmetic on strings. Strings. Okay. So that's sort of a basic example of doing some string slicing. Okay, so good here. So exercise for you guys. Yeah, you can do you could do print with commas and it automatically concatenates stuff together. Okay. So I want you guys to reverse a string. So exercise. So let's do word equals something or word. We'll do stuff. So I'll let you play around with this. Give you a couple, 2 or 3 minutes to see if you can remember how to grab the items in reverse order. Yeah. Okay. So we can just do. Anybody have any questions on getting things in reverse order? Good. Okay. So it's an R word equals word, colon, colon, -1. Yeah. Gnitimas. It's Greek. Okay. Okay. So slicing. Okay. So a little recap of slicing just because it's so important. Okay. So make a list. Okay. Yeah. So if you remember defaults, start, stop, step. Okay. So 2 to 4. That gives me all the numbers between 2 to 4 and step size 1. This one, 2, blah. Okay? I did not put anything. So the default is to the end. So if you do 2 colon, default is it starts with 2, goes to the end. Nums, blah, default is start, default is end, default in step size. That's a whole list. Okay. Reverse order, -1. You can assign slices of lists. Okay. That's another good example. So we do L. Okay. So I want exercise for you guys. I want you to reverse items 2 through 4. Make a list that is L that goes from 0, 1, 4, 3, 2. Okay? So let me do assigning slices. So you do S LL equals L. So now LL, it's a straight copy of my original list. Okay. So I can do LL, and then I can assign a slice in here. So I can do no, okay. So that's a slice I want to replace. LL 2:5 equals. And I'll let you play around with this. Give everybody maybe 2 or 3 minutes to play around with this. Okay. So yes, yes, there we go. Okay. So let's pick that slice out of here in reverse order. So we have that slice. So let's look at what that slice looks like in reverse order. Okay. So let's do L will go to my original list. Okay. Let's do 5:2:. -1. It's just a guess. Just a guess. Ah, that's close. It's close, but it shifted 1 over. Remember, when I'm going in the reverse direction, bump the count by 1. Okay. So four. Okay. So right. So starting at 4, down to 1 in reverse order. Okay. So what I can do here is I can do L. No, I'm going to modify the list in place. L 2:5 equals L 4:1:-1. Yeah, good. I reversed a slice of that list. So, doing a little recap here. So yes, slicing, it may seem intimidating with all these little colons and so forth, but three things you have to remember. Start, stop, step. Start defaults at the beginning, stop defaults at the end, step defaults at +1. Okay? If you know what they are, start, stop, and step, and if you know what they default to, you can pretty much do, actually not pretty much, you literally can do any combination of the number, slicing. Okay? Okay, so went over this. Strings and tuples, they are both immutable. Once you've created a string or a tuple, you cannot change the values in them. So we showed it gives you an error. Okay. So 4, we went over 4, so it's 4 item in a range. Pretty good at that, I think. So let's take a look at these two code snippets. Both of these do identically the same thing. Okay. So we have the first one. We make a string here, and we do 4 index in range len s. Okay. So we explicitly grab the index item and we check if it's there, or s is equal there, and we print that out. Okay. But we don't have to do all of that explicit indexing with a 4 in. Okay. So we simply have to do 4 char in s. If char is this or if char is that, do something. So take advantage of that iterating over a thing in a collection. Okay. So again, 2 more code snippets that do identically the same thing. Okay. Doing it this way is both ugly and error prone. Remember, something that a very smart guy, my first real boss, Ken, he told me something really, really profound. Every additional line of code you write is a chance for an additional error. Okay? The more code you write, the more likely you are to write an error. And that's why it's a really good idea to write as cleanly and as concisely as possible. Try and do things in as few lines, because the fewer lines you have, it's easier for somebody else to read it, it's easier for you to read it, and it's less likely to make a mistake. So avoid doing things like this for while I is less than n, char equals word. Avoid doing that, and just simply take advantage of what the language gives you. For char in word, do stuff. You don't have to worry about grabbing it. You don't have to worry about incrementing counters. Each one of these additional things is another chance for you to write an error. So I'll give you guys a little exercise. I want you to write a doubly nested loop like this and print the common characters of the string. Okay. Let's go ahead and copy this down and see if we can get it. Now go ahead. Oops. Typo. Okay. Yeah, so you can see it spit out a lot of stuff because this was a double loop. So what went on here is it's sort of the outer loop here, and that's the outer loop is going to go over T, I, blah, blah, blah. And then the inner loop, you're going over the outer loop, and then the inner loop goes over each one of those individual elements. So how many actual comparisons do I perform here? So if the number of characters in S1 is N, and the number in S2 is M, how many comparisons do I perform here? Okay. So if we start off with the top one, we got M characters. One, we check all the other ones. We go to M characters in the other one. We go to the next one. Go to one. Check all the other ones. Go to the next one. Check all the other ones. So how many times does this actually, how many times is this statement here called? Any guesses? Yes, M times M, yeah. So this is, yeah. So each time we have a nested loop, we multiply however many times that executes by all the outer ones. So if we have a four-way nested loop over N, M, L, K, our total number of times that loop is executed is N times M times L times K. Yeah, okay. Okay. So let's go back to our little math example. Do a little bit of a root finding here. So the guess and check, that's one of the most common ways we have numerical algorithms work, where we guess a solution and then we check how good that solution is, And if it's not good enough, then we try and refine that guess. Okay. So we can do a cube root here, where yeah, so we can do a kind of a little dumb approach. A dumb approach would be, when we look at a cube root, we know that the cube root of a number has to be less than that number itself. Okay. So what we can do is we can exhaustively check every element that is less than that. So let's do that. So we can do cube eight for yeah. Okay, so we got that. Not a terribly efficient way of doing things, because we have to check every element in there, and this will, well, it really won't work when we're dealing with floating point numbers. So let's try and be a little bit smarter about this. Okay. So we can refine that a bit, and then yeah. So this one here, we're checking if we have a perfect cube, and giving us a little safety break of exiting out of there. Okay. So this leads us to the idea of approximate solutions of actually not leads us, this gets us back to the idea of approximate solutions, where we come up with a guess, and we keep refining the guess up until we get to what we consider good enough. And again, I really can't stress this enough, that when we're dealing with anything numerics, anything that we represent in a computer is fundamentally an approximation. It's never going to be exact. And you may ask yourself, well, how good does my solution have to be? Well, it really is a judgment call, where if the problem you're modeling, you have a lot of uncertainty, well, you probably don't need to have 100 digits of precision if your model is not all that good. But a lot of times you can have something that's good enough. So what we do with an approximate solution, we start with a guess, and we increment that by a small value, and we keep guessing. Is the guess cubed minus the cube? We check, is this value good enough? And if it's good enough, then we can go ahead and break. Okay. So let's go ahead and type in this. Okay. So, you know what? I'll leave that as an exercise for you guys. Let's do that as an exercise. So the answer is on the next slide. So try not to peek at the slide, okay? let's do that as an in-class exercise. So we can say, is that solution good enough? So the entire algorithm is here. The description of it is here on the slide. Let's see if you guys can come up with this answer. Practice. Any questions here? So how you guys doing? You want me to give you a hint, answer, or would you like to play around with this some more? It's up to you guys. Okay, so let's take a look at how we do this. So one way we can do this, as a simple way, is I did it with a while loop here. So let me go ahead and type this in and show you guys how it works. So I did a cube. I'll just do 28 on that. Epsilon one. I'll do plus one. Increment. Yeah, that so let's take a look at what's going on. So while absolute value of guess cubed, right? Minus cube, minus the cube of what I want is greater than or equal to epsilon, yeah, and is less than or equal to cube. And I can guess x equals, I'm increasing my guess by the increment, and x equals 1. Okay. If so, the absolute value, so redoing my test condition here. Okay. So I'm gonna, so go ahead, I written this up. So I sort of have my cube is 28. And then I'll go ahead, I'll make it really easy for it to find it. I'll make my epsilon big. Okay, how about if it's within 5? Let's see. I don't know, change this. I don't even do that. Okay. Okay. Let's go ahead and run this. Okay. So I'm going to start off my cube of 28. My epsilon's 5, so that's going to be a pretty big number. So that's going to make it pretty easy to find. I'll start off my guess 0, and then I will increment it by 0.1. Okay. So what it's going to do here is going to do while absolute value of guess cubed minus the cube. So that's the difference. If that's going to continue, if that's greater than epsilon and the guess is less than cubed, and I'll keep increasing the guess by that increment and increasing my count. So we'll run this. So that typo variables I and C R. Okay, so let's see what happened here. So if we look at the code here, it starts off with a guess, initial guess as 0.1. It keeps increasing that guess by 0.1 each time. And then bump, 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 bump. And then it made 29 guesses here. I finally got to a final answer of about 2.9. And it says, hey, that was close enough. Okay. So what do you think? So if I make my epsilon smaller, that means it should give me a more accurate answer, right? I'll make my epsilon 1. Yeah, okay. So this one, we need to overstep it, okay? So it still did about 30 guesses, but it zeroed in on a closer answer. But what I'm limited here is by really my increment. If I make my increment smaller, oh, why do we choose num guesses? Actually, that's n guesses. So n guess. This is our count of how many guesses we've actually made. So cube here. That's the we're looking for the cube root of this number. Epsilon is how close we want to get. Okay. Guess, that's our initial guess. And increment, that's however much we increment it each time. And then n guess, that's how many guesses we've actually made, right? So if I run this again with a smaller epsilon, 0.5, I'll take a little longer. Okay. So I made 280 guesses. Okay. And then, I think I got an issue here. Oops, I made a typo. Okay, that's better. Okay. So I just slightly overstepped. I just did slightly over my answer. So we got answers 3.1. It's cube root of 28. Let's do 27. No, it's supposed to be 3. Okay, just a little bit over. Okay. But if I wanted a closer answer, 2.6. This will go really slow. So it did get me pretty close. It got me within 0.1. But I took 295 guesses. It's quite a few number of tries to get here. Okay, this is not really the most efficient approach of incrementing each time. But we can actually do a lot smarter than this. We can do what's called a bisection search. So basically what we do here is instead of starting at the beginning and searching every possible answer up until I get there, we're smarter. Oh, what is plus equal? Oh, okay. So plus equals means I increment. So okay. So if I have A equals 1, then I do A equals A plus 1. That assigns a value of A plus 1, but plus equals is a shorthand. So A plus equals 1 is completely exactly identical to A plus 1. It's just a little shorthand. Okay. Okay. So we want to do a smart search. So we can improve our search by A, coming up with a better initial guess, and B, instead of exhaustively searching all the way, we can apply a little heuristic saying, hey, if we come up with a guess, then we can ask the question, is that guess bigger or smaller than the actual real solution? Because we can ask that question. So that's what's called a bisection search. So each time we make an initial guess, the next guess either goes one way or the other. It doesn't, because we know that if our guess is bigger, okay, we need to search the lower half. If our guess is higher, okay. So that allows us to keep zeroing in on a range. So now we can rewrite this using what's called a bisection here. Okay. So let's see what we're doing here. So we do our same basic cube root search, okay? But we start off our guess as the average of the high and low values. So we know, when we start here is we start with our cube. Our cube, we want to get the cube root of this thing. Or epsilon, we want to go within 0.01 of this. Then our low range, we know that our answer has to be greater than 0, and we know that our answer has to be less than cube. So we know that our answer has to be somewhere within that range of low and high, right? Okay. And then we don't know where exactly in that range our answer is, but we know it's somewhere in there. So let's just come up with our guess as halfway, exactly in the middle. So our guess is the average or the midpoint of high and low. So let's go ahead and write this in. So we have cube equals 7. Okay. So while absolute value, we asked the same question before. Yes. Cube greater than or equal to epsilon. Okay. So now we see, does this value, is it less than or greater than where I want to go? Okay. So we can do if yes, less than cube. Well, what goes on here? If it's less than cube, okay. So that means that's my new low range, okay. Okay, yeah, so my low because I know that the real answer, I know it because my guess is less than the actual answer. So where the real answer has to be is greater than this value. Okay? So I chop off the low range. Okay? And I do else we do the same thing. Yes, equals then I'm going to do, let me print out a little more diagnostic info here. Okay. So print out some diagnostic information. Then, my loop. Okay, so let's see what I got here. So we ran this, okay? So it only took us 14 guesses. It took us 14 guesses to get to our real answer. Okay? So let's see. Yeah. So let's see what happened here. So we got guess number one, the low is 0. The high, yeah, so we go through this. So we found that our low, we kept low, and it was below that. So we chopped our domain in half. We chopped our high, we brought our high down to the midpoint, and then got our next guess. The next one, it was still above it. So we chopped our high point, we halved our high point. We halved our high point, so we kept chopping that domain down. And then now, we saw that our at this point, on our fourth iteration here, okay, we saw that our guess was less, the cube of our guess was less than the answer. So that means we need to increase the bottom range. So I bumped up my bottom range, and then I kept bumping up my bottom range, bumping this up, and that allowed me to zero in. And then zeroed in a little closer, zeroed in a little closer, and finally got here to guess. I'm not sure that 437 came from, but anyway, yeah. So that allows us to keep chopping our search space in half, keep halving it. And it only took us 14 iterations to get to a really good answer. Okay? So, who's got some questions on a bisection search? Okay. Looks like everybody's probably don't see any questions here. Okay. I am watching the chat here, so if anybody has any questions, please post them. Oh, break? Okay. Yeah, this sounds like a perfectly reasonable time for a break. Okay. So why don't we, let's see, how many more slides do I have in this one? Okay. Sure. So yeah, we can go ahead and take a break. Why don't we go ahead? Actually, would you guys rather do a break or more of a lunch? How long of a break would you lunch? Okay, got it. Okay. What do you think? Half hour? Okay, great. Okay, so we'll go ahead and take a half-hour break here. So I have 2:50 EDT. So let's go ahead and I'll go ahead and be back here at about 2:20. Okay, so about half hour. Yeah, 3:20. Yeah, today we will go till 6. Actually, I believe we're on Eastern Daylight. Yeah, daylight time. Yeah, I wish they did rid of this daylight stuff. Okay, great. Okay. So so I'll keep watching the chat here if anybody has any questions, and I guess we'll be back here in a half hour. Okay, great. So welcome back, folks. So I guess we can, if everybody's back, I guess we can go ahead and continue on. Yeah. Okay. Um, okay. So we basically left off a half hour ago looking at the looking how a bisection works. So we can look at the convergence here, where basically it's having our domain each time. So it's a lot better way of doing things. So you know, I think I'm gonna skip a bit of the analysis here. We maybe cover that a little bit more next week. Um, okay, so again, loops, four in. That covers all the items in it. Occasionally you'll run into something where you'll want to write a for loop, but you'll also want the index of something. So occasionally you'll want to do something like this, where you can do for index comma thing in things in enumerate. And what the enumerate does is that gives you back basically a pair of things. That gives you back the index of where it's at and the thing itself. So you'll probably pretty rarely want to do something like that, but it's there if you need it. So let's start off with right away an exercise. So we have two lists here, A and B. And then I want you to write a program that returns a list that contains only the elements that the two have in common without duplicates. Okay? Let's go ahead and start that. And I'll give you a couple little hints. I'll give you a couple little hints, okay? So if I make a list A equals we use the word in loops. You can also use that as a conditional. One in A. You can also use the word in to ask the question, is something an element of something else? So you could do 10 in A. That's false. 2 in A. That's true. So, and then to add elements to a list, okay? To basically build up a list, you can do B equals an empty list, right? And we could do B plus equals 5. Oops. Okay. This will be a little introduction to the notion of objects. Okay, so everything in Python is an object, and a lot of times objects will have various functions attached to them, and we typically refer to these as methods. Okay, so one of the methods that list has is append. Okay, so you could do B, and I'm just pressing the dot here. And if you hit tab, that'll give you a pop-up list of all of the methods that are attached to that object. So you can do append, clear, count, index, sort, various other things. Well, the one we'll be doing a lot is append. So to add an item to a list, we can add an item to a list basically one of two ways. You could do b dot 0 and add it. Or the other way, you can actually concatenate two lists together. So you could do B, you could do something like 1, 2, plus if you have two lists, you can stick them together using the plus operator. But that only works when you have two lists. The plus only works between two lists. The plus doesn't work if you're trying to add an object to a list. So if you want to add an individual object to a list, you have to use append. Okay, so using these little tidbits, they should give you just enough information to complete this exercise. So let's go ahead and give this a try, yeah? Okay. Okay. Well, it looks like we got some answers. So why don't I go ahead and show you what's going on here. So remember, and I asked you to do two things here. So I'll run a program that returns a list that contains only the elements that are in common with the lists. So we're looking for two things here. A, the elements that are in common, and B, making sure that they're not duplicates, okay? So we already figured out, we already went over an example of how to check if the two elements are in common. Well, that is if I equals j. Okay. So this one, remember, the first loop goes over all the elements in A. And then the second loop goes over all the elements in B. So we basically end up doing n squared comparisons here. And in this first comparison, this first comparison here, if I is equal to j, that will be true if those two elements are in common. Okay, so that's first one. So B, we don't want any duplicates, remember? So how do we check if an item is already in the list? What was the thing that I just went over like literally 5 minutes ago? What's the keyword I use? Starts with an I and ends with an N, right? Yeah, that'll be N. Okay. And so here, because they're both equal to each other, it doesn't matter which one I compare. So I do if I in and not I result. Okay. Then I can do result equals result plus I. Okay, that's pretty simple. So if I in J for I in A, for J in B, if the two elements are equal and they're not already in the list, they're not already in the result, then I simply do result equals result and adding a new list that contains only that item to it. Okay. It will be this will be completely equivalent. Result dot and I. That'll be totally equivalent. And that. What I did here, I put a hash sign there. A hash sign in front of any statement that makes it a comment. So that's a way to add documentation, add text to your code, and comments don't actually get executed. They're just there to annotate and describe what you've written as the documentation. So we could see this one. Perfectly equivalent, okay? So, questions? Okay, so I think we're good. So, another exercise. Remember, programming, we learn by doing. Right, actually, I'd like to write them two cells here, okay? So, one cell that takes A and reverses it using slicing, and another one that creates another list by iterating over the elements in it. Okay? So slicing, I'll let you try and remember how we do. Thanks for that. And then I'll give it a little refresher here. We can use range to find an index, and then we grab individual items out of a list by doing A1, A, okay. You can grab individuals out of it using the little the square bracket indexing. Okay. So we're both slicing and indexing. And remember, the arguments to range are the same arguments if you would give the slice colon operator. So start, stop, step. But the slice ones are nice is because they automatically give you the beginning and end. So let's do a reverse. So reverse should be pretty easy, right? So we have I'll just do this A. Remember, A is just colon, colon, -1. Okay. Remember range. Range is the same way. So we can do, I'll go ahead and show you the indexes. We have list. So we want to start. And that would be len A 0. So that gave me indexes of 10 down to 1. That's not quite what I want. Okay. So we can do 1. This is why graphic is kind of goofy. Then A 1. So if I can do range and make that one create the indexes descending. Okay. So that means what I can do with those is I can do result equals I. I can do result plus equals A okay. So I made a for loop here where I iterated over the indexes in reverse order, and I manually copied the value out of A. I pulled that value out, I created an array, and I concatenated, or I appended these two arrays together into result. And we can see that A default start, default stop, negative is a lot cleaner than trying to remember all this stuff. Okay, so conciseness. Okay. So well, we're going to get to referencing things here in a minute. Okay. So okay, so one thing, I think maybe I'll go ahead and bring this up here. Okay. So we have, I got another slide that I'm going to talk about this a little later on, but I want to talk about values versus referencing. This is something you might have heard thrown around, but we have A, okay? A is just a name. It's what we call a symbol. And that symbol refers to this actual list. And that list, it exists somewhere in memory. We don't really care where it lives. All we know is we know that this A is a name that refers to that thing, okay? So we can also do B. B is another name, but we can change what B refers to. Or we can do B equals A, okay? So now we have A, B. Okay. So now both of these guys refer the actual same thing. The important thing to remember is what I've done here. I did not make a copy. What I did is B is both of these guys, both of these names, A and B, they're just names. They refer to the same thing in memory. Okay, it's names in a programming language like Python. They're subtly different than the idea of a variable in math, because in a variable in math, you always store the value in it. But in programming, they're really just names that refer to things, and they very often refer to the same thing. So if you'll notice, I'll go ahead and modify A 0 equals, you know what? I'll give it a string. A. So now the first object in A is a string, but B refers to the same thing, okay? Now to get an actual copy, to make an actual copy, what I do is this. I do B equals A, and I grab a complete slice out of there. Okay. So I can do B and A is left alone, okay? So when I grab a slice out of something and I sign out to value, that's actually making a complete copy of the stuff I pulled out of there. But if I just have two names that refer to the same thing, this little caveat that is and that's why I was a little hesitant of using the term variable to refer to names, because like I said, variables in math are subtly different than names in a programming language. Okay. So let's go ahead and we'll start the 4.